All right, everybody. Mr. Bucko here with solving absolute value inequalities, and we're going to do that graphically, and then we'll do it algebraically. So we'll start with graphically, which is a kind of a tedious process, but we can at least see and visualize what these answers mean for absolute value inequalities. So to solve the absolute value inequalities, graphically, we're going to take the single inequality and separate it into two equations. So it's not a typo. We're going to do two equations, and then we'll graph the two equations, which we know how to do, and then we'll figure out where to shade just based on what the inequality says. So what does this mean? Let's say we have the inequality, absolute value inequality, of the absolute value of x plus 3 plus 1 is greater than 4. So the first thing we're going to do here to solve this graphically is we're going to take the single inequality and separate it into two equations. So that looks like this. So we're going to graph f of x. We'll call the left half f of x, absolute value of x plus 3 plus 1, and then we're going to take the right half, g of x equals 4. So we know how to graph these things. We did that in E2, I believe it was, where we graphed them, and then those are the two graphs of the inequality. What we're asked here, or what the inequality is that the inequality is in the form f of x is greater than g of x. So this part right here is bigger than this part. So I'm going to look for the intervals on the x-axis where that graph is above the other graph. So I have them color-coded here. So here's f of x. So where is the blue graph above the red graph? Well, it starts about right here. It's kind of that boundary point, and then from x equals 0 on, the blue graph stays above the red graph, or f of x stays above g of x. And it also stays above g of x over here, which is, looks like negative 6. So the solution to the inequality then is x can be less than negative 6 because everywhere from here on, the blue is above the red, or x is bigger than 0 because everywhere from here on, the blue is above the red. So we can kind of see exactly where that is. So that means that we can take any numbers that are bigger than 0, plug them into this inequality, and it'll be a true statement. Or we can take any number that's less than negative 6, plug it into this value for x, and this inequality will make sense. So that's what it looks like graphically. It's a relatively simple process, but it's kind of tedious. Draw out a graph and graph the lines, but at least we can kind of see what those solutions are. Kind of helps in that manner. And then if we graph those on a number line, just this is where all the solutions are. So this is basically the x-axis here from 0, and 0 is not included because it's not or equal to. And then negative 6 and below, and negative 6 is not included because it doesn't say that this can be equal to 4. It's got to be strictly greater than 4. So that's what that looks like graphically there. Let's do one more here. So we'll solve this graphically as well. We'll break them down into two equations. And we'll get those on the graph. They look like this. We know what that looks like because the vertex of this absolute value equation is 2, negative 3. So then we have that there. And we have the slope of 1 on the right side, slope of negative 1 on the left side. And then we have g of x equals 1 right here. So the inequality is the form we want the blue f of x to be less than g of x. So we're looking for, well, where is the blue curve or the blue function below the red function? And it starts, looks like here at negative 2. Because as we go this way, that blue is still below the red. And then that stops at 6. So what happens here is we have an and situation. So the solution is x has got to be bigger than negative 2. And it also has to be less than 6. So this isn't or, because it can't be bigger than negative 2 or less than 6. It's those two values are in between each other. This is an and situation. So what that looks like on a number line is like this. So we have negative 2 to 6, and neither of those are colored in. Those negative 2 and 6 are not solutions because this inequality is not equal to, it's strictly less than. How do we do it algebraically? Let's do this algebraically real quick here and see what this looks like. So we have an inequality here, and all the work's already there. So I'll just kind of try to go step by step through what this looks like. 3 times the absolute value of x minus 7 is greater than or equal to 9. So we're going to isolate that absolute value portion just like we did with the equation. So that's what's happening here. We just divided both sides by 3. So divide by 3, divide by 3. Then you get the absolute value of x minus 7 is greater than 3 because 9 divided by 3 is 3. And now that's gone. And now from here, what this means is that x minus 7, the absolute value of x minus 7 needs to be bigger or equal to 3. So what that means is that x minus 7, this value needs to be bigger than 3 because any number that's bigger than 3 has an absolute value that's bigger than 3. Or x minus 7 can be less than negative 3. That's where this comes from. Because any number that's less than negative 3, like negative 4, negative 5, negative 6, also has an absolute value that's bigger than 3. So that's why we have these signs kind of flipped around here, is because of the fact that this is going to be bigger than this value. So we want those negative numbers that are bigger than 3, so to speak, which are actually less than negative 3. And then from here, we just solve algebraically. Just add 7 to both sides. So x can be greater than or equal to 10, or x can be less than or equal to 4 from solving this inequality. So what that means is that any number that's bigger than or equal to 10 can go in for this x, and this sentence will be true. Or any number that's less than or equal to 4 can go in here, and this sentence will also be true. What does that look like on a number line? It looks like this. X can be bigger than or equal to 10, so that's from here on. Or x can be less than or equal to 4, which is from here on. Another one. Absolute value of 2x plus 3 is less than 5. So we already have that absolute value expression by itself here. So we have to say, well, what numbers can go in the absolute value? What numbers have an absolute value that is less than 5? Well, those are numbers that are less than 5, like 4, 3, 2, 1. But they're also numbers that are bigger than negative 5, which means negative 4, negative 3, negative 2. Because those values also have an absolute value that's less than 5 as well. So notice again, we kind of have that flipped around sign a little bit because you have to understand what this inequality means, and we only get positive numbers out of the absolute value. So we have these two equations, or inequalities, that is, to solve. And we solve that algebraically, subtract 3 on both sides. Subtract 3 on both sides, you get 2x is less than 2. 5 minus 3 is 2. Divide by 2, x is less than 1. And over here we have divide by 2, x is greater than negative 4. So we have and here, and it's and because these two numbers, x has got to be in between these two numbers. X needs to be less than 1. X has got to be bigger than negative 4. Those two are in between each other, so x has to be in between negative 1 or negative 4 and 1. And notice that these circles are not colored in because this is not an or equal to situation. It can't be those numbers. Those are the limits or the boundaries of that, and that's what those look like. Let's do one real world example here. Wrap this up. A box of cereal. I did the box of cereal example because I like cereal. So a box of cereal is supposed to weigh, one particular, 13.8 ounces. Probably just made up. I don't know if that's real or not. But it can vary as much as 0.1 ounces or 1/10 of an ounce. Because when you're filling up the cereal boxes, you might have a little bit more or less. The weight isn't precise every time. We want to write and solve an inequality to find the range of acceptable weights. So what is the acceptable weights? It can vary 1/10 of an ounce. So it can be more than 13.8, or it could be less than 13.8 by 1/10 of 1 ounce. So what that looks like is whatever the weight is, whatever the weight of the box is, if we subtract 13.8, that absolute value has to be less than or equal to, because it can vary 1/10 of an ounce, 1/10. So this weight, whatever it is, if it's 13.2, if it's 14.1, if it's whatever that weight is of each box, because they're not exactly the same, you take away 13.8, that difference between these two numbers has to be less than 1/10 of an ounce, and we're going to take the absolute value so that we're dealing with positive numbers here. So now we solve this absolute value. Well, W minus 13.8, this value needs to be less than 1/10, or it needs to be bigger than negative 1/10, because anything that's bigger than negative 1/10 will have an absolute value that's less than positive 1/10. The confusing part of the absolute value there. Now we have these two inequalities to solve. And now it's basic algebra from here. Just add 13.8 to both sides. In this case, if it's less than 1/10, it could be 13.9, or it could be 13.7. And that could be, it's probably rather intuitive, which is what we're given here, but this is how we solve this type of equation or inequality with absolute value. So the box of cereal could weigh as much as 13.9, and it has to weigh at least 13.7. So the weights have to be in between there. So we can write that as W has to be in between these two values, and it can be those values because 1/10 is okay. And that is how we solve absolute value inequalities, both graphically and algebraically.